Hello, this is the Mathematic Fanatic, and you are watching 3 cool Diophantine equations. So sorry for not posting more recently. I have been sick with a cold, so now that I'm feeling better, I plan to post more. So let a and b be integers such that a and b are greater than or equal to 0. Then we want to find every a and b such that 4a plus 2 to the a equals b cubed plus b factorial plus 2. To solve Diophantine equations, we would want to bound the possibilities within a finite number. The way I will do that is the following. For a equals k plus 2 greater than or equal to 2, then 4a plus 2 to the a equals 4 times k plus 2 plus 2 to the k plus 2, which equals 4 times k plus 2 plus 4 times 2 to the k, which equals 4 times that whole thing, meaning that it is divisible by 4. However, if we take b equals 2n plus 1, which is greater than or equal to 3, then b cubed plus b factorial plus 2 is odd, because 2n plus 1 all cubed equals 8n cubed plus 6n squared plus 6n plus 1, which you can factor out a 2 from all of the higher order terms, except for the 1, and then that will just equal 2m plus 1, where m is all those higher order terms. And b factorial is even because for b greater than or equal to 3, there's a factor of 2. So we get an odd plus 2 evens, because 2 is an even number, which makes an odd. If we take b equals 2n, which is greater than or equal to 4, we get b cubed plus b factorial plus 2 is not divisible by 4, because 2n all cubed equals 8n cubed, which equals 4 times 2n cubed, which equals 4m. And b factorial is divisible by 4 because it has a factor of 4 in it. And the number 2 is not divisible by 4. So 4m plus 4j plus 2 equals 4 times all m plus j, all plus 2, which is not equal to 4d, where d is an integer, which means we are left with two strictly increasing functions that are bounded by b is between 0 and 2 inclusive, which means we check every case b equals 0, b equals 1, and b equals 2 to find that for b equals 0, we get 0 cubed plus 0 factorial plus 2 equals 0 plus 1 plus 2, which equals 3. And for a equals 0, we get 4 times 0 plus 2 to the 0 equals 0 plus 1, which equals 1, which is less than 3. So we increment a to a equals 1 because it's strictly increasing, so it goes up. We get 4 times 1 plus 2 to the 1 equals 4 plus 2, which equals 6, which is greater than 3. Now we need to increment b, because that is now less. So, therefore, b equals 1, and we get 1 cubed plus 1 factorial plus 2 equals 1 plus 1 plus 2, which equals 4, which is still less than 6. So we need to increment b one more time, which is the final value that it can be, which is b equals 2, to get 2 cubed plus 2 factorial plus 2 equals 8 plus 2 plus 2, which equals 12, which is not equal to 6. So now we need to check a equals 2 or something higher to get 4 times 2 plus 2 squared equals 8 plus 4, which equals 12, which is exactly what we're looking for. Therefore, the solution a equals b equals 2 is a solution. And since both functions are strictly increasing, we know that when a is greater than 2, then 4a plus 2 to the a is greater than 12. And since b is between 0 and 2 inclusive, 2 is the only solution. So our second problem. Let a and b be integers such that a and b are greater than or equal to 0. Then we want to find every a and b such that a squared b plus b cubed equals 2 to the a. Therefore, also, b times a squared plus b squared equals 2 to the a, meaning that b equals 2 to the k, because the only prime factors of 2 to the a are 2 with multiplicity a. This also means that a squared plus 2 to the 2k equals 2 to the a minus k. And that's because I can divide out the 2 to the k from both sides. To make this a finite set of possibilities, we can test a is less than k, which would give us the following. A squared plus 2 to the 2k equals 2 to the a minus k, which is less than 1, which is equal to k squared plus 2 to the 2k, which I'll explain in a few sentences. Therefore, we can rearrange the equations to get k squared minus 1 equals k plus 1 times k minus 1 by factoring, which equals negative 2 to the 2k. And that's just from rearranging this part right here. Meaning k is less than 1. And if k is less than 0, then b to the k is not an integer. So we get k is strictly 0. Therefore, if a is less than 0, that gives us a contradiction, because it's the positive or non-negative integers. So a must be greater than or equal to k. Then we get a squared plus 2 to the 2k equals 2 to the a minus k, which is greater than or equal to 1, which equals k squared plus 2 to the 2k. And we get all that, and here's why we get in both sides. Since when a equals k, it is the lower bound, it is the upper bound for the other one. But that gives us 2 to the a minus k equals 2 to the k minus k, which equals 1, right? Which equals k squared plus 2 to the 2k from the previous thing, which equals a squared plus 2 to the 2k. So that gives us our kind of bound. Therefore, k still equals 0 by the same reasoning. So b equals 1, which means that we get a squared plus 1 equals 2 to the a. We know that a squared plus 1 is greater than 0, so we can take the logarithm, base 2 of both sides, to get log base 2 of a squared plus 1 equals a. And we can take the original equation in the following way. A equals the square root of 2 to the a minus 1, because that's just rearranging it a little bit, so the a squared is by itself and then square rooting. And we know it's positive, so we don't need the plus or minus. So then we can set them equal to each other and get log base 2 of a squared plus 1 equals the square root of 2 to the a minus 1. And that's because they're both equal to a. And the square root function increases faster than the logarithm function after a certain point, so they are only equal at one point after the square root overtakes the logarithm. As well as 2 to the a increases faster than a squared. Therefore, we can find the rate at which it takes over by plugging in successive values of a, subtracting them, and seeing the difference. For a equals 0, we get log base 2 of 0 squared plus 1 equals log base 2 of 1, which equals 0, which again equals 0, which equals the square root of 1 minus 1, which equals the square root of 2 to the 0 minus 1. That shows that they're equal, so we don't need to worry about that. So since they're equal, we get that as a solution, right? So, which means a equals 0 and k equals 0 is a solution, giving us a equals 0 and b equals 1 is a solution. That's just one of them. We don't know if there's more, but we want to show that there is or there isn't. So testing a equals 1, we get log base 2 of 1 squared plus 1 equals log base 2 of 1 plus 1, which equals log base 2 of 2, which equals 1, which again, we can set equal to 1 because it's the same, which is equal to the square root of 1, which is equal to the square root of 2 minus 1, which is equal to the square root of 2 to the 1 minus 1. Therefore, that gives us another solution of 1, 1 rather than 0, 1. So now we have 0, 1 and 1, 1 as our two solutions. Let's see if there's any more. Let's check a equals 2. We get log base 2 of 2 to the 2 plus 1 equals log base 2 of 4 plus 1, which equals log base 2 of 5, which is greater than 2 because log base 2 of 4 is 2. And then that's also greater than square root of 3 because square root of 4 is 2. So it equals square root of 4 minus 1, which equals square root of 2 to the 2 minus 1. So that means that log base 2 of 2 to the 2 plus 1 is strictly greater than square root of 2 to the 2 minus 1. Okay. There could still be possibilities, because the rate of change is greater for the logarithmic portion, which we still know the square root portion takes over eventually. So test a equals 3. We get log base 2 of 3 squared plus 1 equals log base 2 of 9 plus 1, which equals log base 2 of 10, which is strictly greater than 3 because log base 2 of 8 is 3, which is greater than the square root of 7 because square root of 9 is 3, which is equal to the square root of 8 minus 1, which is equal to the square root of 2 cubed minus 1. Okay, so that means log base 2 of 3 squared plus 1 is strictly greater than square root of 2 cubed minus 1. Therefore, there could still be another point when the square root overtakes the logarithm. So let's check a equals 4. We get log base 2 of 4 squared plus 1 equals log base 2 of 17, which is greater than 4, because the log base 2 of 16 is 4, and which is greater than the square root of 15, because the square root of 16 is 4, which equals square root of 16 minus 1, which equals square root of 2 to the 4th minus 1. So we could still have another point when it gets overtaken. So check a equals 5. We get log base 2 of 5 squared plus 1, which equals log base 2 of 26, which is less than 5, right? Because log base 2 of 32 is 5, which is less than square root of 31, because the square root of 25 is 5, which equals the square root of 32 minus 1, which equals the square root of 2 to the 5th minus 1. Therefore, since it was overtaken, we know that the difference was larger for the square root function. However, we do not know that the logarithmic function will not overtake again. So we'll use the derivative of each side to find out if it will or not. So f of x equals log base 2 of x squared plus 1, and g of x equals square root of 2 to the x minus 1. And we get f prime of x equals 2 times ln of 2 times x all over x squared plus 1. And g prime of x equals ln of 2 times 2 to the x over 2 times the square root of 2 to the x minus 1. So if we find when f prime of x is less than g prime of x, we can see what values that is true. Multiplying it out a bit, we get 4x times the square root of 2 to the x minus 1 is less than x squared plus 1 times 2 to the x. We need to find what x values that's true for. So if we plug in the value x is greater than 5, then 4x is less than x squared plus 1, right? For all of them, because it'll always go greater than. So, and then we know that the square root of 2 to the x minus 1 is always less than 2 to the x. Therefore, g of x wins out for all a greater than 5, meaning the solutions we found are the only solutions, 0, 1, and 1, 1, since we've checked 0 through 5. There we go. The third problem. This one has 3 variables. Let a, b, and c be integers such that a, b, and c are all greater than or equal to 0, such that for f of x comma y equals x squared y minus 9x y squared plus 2, such that f of a comma c equals the partial derivative of f with respect to x and y of c comma b, which gives us a squared c minus 9ac squared plus 2 equals 2c minus 18b, which gives us an easy formula for b, which is 9ac squared plus 2c minus a squared c minus 2 all over 18. Therefore, in order for b to be an integer, 9ac squared plus 2c minus a squared c minus 2 has to be divisible by 18. So we can use the quadratic formula on it to get the following. A equals negative 9 plus or minus the square root of 89 minus 8c all over 18c squared, meaning that c is greater than 0, because if it wasn't, there would be an issue. Because there can't be 0 in the denominator. But if c equals 0, then we know we get another contradiction anyway, because 2 equals a squared times 0 minus 9 times a times 0 plus 2, which equals 2 times 0 minus 18b equals negative 18b, which means 2 equals negative 18b, and that wouldn't end up working out for b, because we know it's an integer, positive integer, or actually non-negative integer. So we know that the case would never work anyway, and we can simplify. A equals negative 1 over 2 times c squared plus the square root of 89 over c minus 8 all over 18. Because if we have a being positive, we must add the square root part, since the negative 1 over 2c squared part is always negative, and we need 1 over 2 times c squared to be less than or equal to the square root of 89 over c minus 8 all over 18. So we end up getting 9 is less than or equal to the square root of 89 minus 8c, which gives us 81 is less than or equal to 89 minus 8c, which finally gives us c is less than or equal to 1, right? I hope that makes sense to you guys. Meaning c equals 1 because we already showed that c does not equal 0. Therefore, a equals 0 based on plugging it back into the formula. And we end up needing to find b, which gives us 2 equals 2 minus 18b, which more simply put is 18b equals 0, meaning b equals 0. So the only solution is 0, 0, 1. Okay, I hope that worked out for you guys. Thank you so much. Have a great day. Bye-bye.